So how are the things in ICER?
It's slowly starting. Some of the
Yeah.
PhD students are back.
Okay,
And
okay, good.
yeah.
So Monica is coming like time to
No,
time?
no, Monica is quarantined. So
Yeah, yeah. I came to know her maid turned out to be positive. Yes.
yeah.
Yeah, but now we are going to hear these kind of cases every day nearby also, because as the number of cases are increasing, it will happen.
Yeah, that's right.
Yeah. So I think it's already 12:04. So maybe we can start now. So good afternoon. Exactly afternoon. 12:04 is there. So I am Rajendra Singh from Department of Physics, IIT Delhi, and I would like you can hear me, na? All of you
Yes.
can hear. Yes. Okay. So I would like to welcome all the participants for this very interesting session. And we have three speakers actually. Not the third one is not somehow he could not attend this one, or he could not come actually like electronically. So the first talk is going to be given by Professor Satyabit Banerjee from IIT Kanpur, and he is going to talk about direct current imaging of a transformation in bismuth selenide topological insulator single crystal. So Satyajit, you have about 25 minutes. So after 25 minutes, I will just inform you. Okay, please.
Okay. So let me set up the pointer once. Yeah. So my screen is being shared. You can see the screen. You can see the
Satyajit,
screen.
you have to
Yeah,
follow
you
the.
have to, Satyajit, you have to unmute yourself, I think.
Oh, okay, okay. I am unmuted.
No, your voice is very low actually.
It was okay while he was chatting with us.
Yes, yes, yes.
So maybe let me switch off the video and see if.
Yeah, I can hear you, but it is very low.
Professor Rajendra, sir,
Yes.
are you there?
Yeah, I am here.
Okay, great. So then I don't have to worry about anything. So chairman is here.
Yeah, I am already here, but our speaker, his voice is not coming is
Can
not
you?
Okay,
audible.
okay. I think it may be mic problem or something.
Can you
Okay.
hear me now?
Yeah, we can hear you now. It's perfect.
Okay, okay.
Yeah, so please.
So sorry for the delay. There was a slight delay. Let me set up the pointer. So there was a slight delay. So thank you for inviting me and giving me an opportunity to present my group's work here. So this is going to be on imaging currents in topological insulators, a technique that we have developed. And sorry, this is the first time I'm giving a talk sitting down, so I will be little fidgety and I might not be able to, it's a little unusual for me to give a talk sitting down. So the talk is basically the work belongs to basically the work done by Amit Jash, my senior PhD student. He's writing his thesis and is going to go for a postdoc. This is Amit Jash. And this has been contributions from Shayantan Ghosh, who is my PhD student, and Ankit Kumar, who has recently left for a postdoc. And the crystals are from IGCAR Kalpakam, Professor Bharati, and his student. And these the work will primarily be from this latest work we have submitted, and it is built on some earlier work that we have done. So the story of topological insulators basically began from 2D systems, 2D electron gases, in which the bulk is insulated. In the presence of a strong magnetic field, you have the quantum Hall effect, where the bulk is basically insulating because of gap Landau levels, and because of skipping orbits on the edges, you have conducting edges. So you have this sort of a state where you have the surface states between the bulk gapped bulk Landau level. So the bulk is like an insulating state with conducting edges. And topologically, this is a distinct state from a conventional insulator. So this insulating state and the quantum Hall state, these states are completely distinct, and you cannot have any phase transition which can connect these two states. Now, this sort of a quantum Hall state is generated with the application of strong magnetic fields. Can you generate similar sort of systems in natural materials? And it turns out that in materials with strong spin orbit coupling, you have similar sort of systems where you have a bulk insulating state, which is shown here, where you have a gap between the bulk conduction band and the valence band, and the gap could be as large as a few 0.1, 0.2 0.1, 0.2 electron volts. And this bulk conducting, the bulk insulating state is actually surrounded by a conducting surface state, a very high conducting surface state. And this high conducting surface state leads to these surface states which are present inside the bulk conduction band. And these surface states, if you look around this point, you will see that they have Dirac-like cone structure. And time reversal symmetry actually, so this is a protected topological state where you have a bulk insulating core which is surrounded by a surface state. And time reversal symmetry actually causes the plus minus k states to have plus minus opposite spins on the plus minus k state. And this actually, for 3D topological insulators, this should give rise to these currents which are circulating with the chiral currents which are spin momentum locked. And so on the surface of this topological insulator, you should have sheets of current, sort of two-dimensional sheets of current which should be flowing. And because both the plus minus spin states are occupied, so therefore an important aspect of this is that there is no effect of disorder. These currents are not scattered by disorder because the plus minus states are both occupied. And you are the one, so therefore you really cannot the disorder really does not cause any scattering of these surface currents which are present on the topological insulator. So these are three-dimensional metals which actually have should have this surface state sitting inside a bulk gapped insulator. And there are such materials. For example, I will be talking of Bi2Se3. There are a host of lot of other materials, but Bi2Se3 is like the silicon of what is like the silicon of the semiconductor industry. Okay, a lot of work has been done, and we focus on Bi2Se3. And the presence of a surface state has been shown through very interesting number of different experiments. One of the interesting experiments is that you can take a nano ribbon of Bi2Se3 and apply a magnetic field along the nano ribbon. This red line shows the magnetic field along the nano ribbon, and you will see oscillations in the magnetoresistance. Okay, and these oscillations correspond to the Arnold-Bohm effect, where there are phase coherent trajectories which are enclosed around the surface. For example, these green trajectories are the surface currents which are flowing, okay, on the surface, and all of these surface current enclose the same area, because the oscillations in magnetoconductance happens at magnetic integer multiples of the magnetic field, which is phi naught, the flux quantum, by the area of this surface enclosed by these trajectories. So it is h cross by E by S, where S is the surface area. So this actually shows that there are conducting surface states on Bi2Se3. Okay. So there are other experiments which also establish the presence of these conducting surface states and a bulk gap state inside the 3D topological insulator. But then people wanted to look at what is the distribution of these currents on the surface. So 3D topological insulators should have this sheet of 2D currents which are distributed on the surface. So people use scanning Hall magnetometry, or scanning squid magnetometry, in fact, to look at the distribution of these currents on the surface. And what they see is that, for example, here you have a Bi2Se3 film, okay, and if you look at the edge of this film, so you do scanning Hall over the entire surface, and you will see the current distribution, because the current generates a magnetic field, and that magnetic field is picked up by the squid loop, okay, and pick up coils of the squid, and then you can see the distribution of current. Now, what they saw was that at the edge of these films, there is strong edge currents. These are not like 2D currents. These are very strong edge currents. Okay, so at the edge of these films, you have strong currents, but inside, as you go inside the film, you don't see a sheet of uniform 2D current, but it is all concentrated along the edges. So these look almost like 1D like current channels which are flowing at the edge of this film, and they don't look like 2D uniform sheets of current. So this was one question which was puzzling us, that if it is a 3D topological insulator, you should have a 2D uniform sheet of current. Where has this sheet gone? Okay. So this will be the questions that we will try and address, is that where are the 2D surface states in a 3D topological insulator? And when we look at Bi2Se3 type of samples, there is a very important effect which happens in these materials, is that there is selenium vacancies. They actually charge dope the bulk. So this is the surface of Bi2Se3, where actually these triangular defects in STM images actually show the presence of selenium vacancies. And when there is selenium vacancies generated in the bulk of the material, they actually generate electronic charges, electrical charges in the bulk. And then if you send in current, the current not only goes through the high conducting surface states, which are shown in yellow, but also goes through the bulk of the material, because now the bulk is no longer insulating. Doping by the selenium vacancy actually intrinsically dopes the system, and you get conductivity even in the bulk. And this was shown through experiments where without doping, if you have selenium vacancies, the conductivity turns out to be metallic. But if you actually kill these by anti-doping, you can actually remove these dope vacancies, and then you can show that you will again make the bulk insulating. Okay, so from conventional transport measurement, it is very difficult to actually make out is the conduction through the surface state or through the bulk, okay, in 3D topological insulators. So there is this additional complication that in topological insulators, you also have the bulk which is conducting. So we wanted to address this question and look at the distribution of currents directly. We wanted to image the currents directly on single crystals and thin films of Bi2Se3. And so let me go on to the results. So so we want to directly image the currents which are on single crystals and thin films of Bi2Se3. So the technique that we use is a modified version of magneto-optical imaging technique, which we have been working on it for a very long time and improving it in various ways. So basically, the technique is normal Faraday rotation, but with very high sensitivity. You come in with a linearly polarized light, which reflects from the surface of a sample, and the polarized light undergoes a Faraday rotation. And the angle by which it undergoes a Faraday rotation is proportional to the local field that is present in on the material. And we image the intensity of the Faraday rotated light. Now this angle depends on the local field. So typically these could be magnetized structures on the sample, but instead of a magnetized structure, suppose the local field is generated by the current itself. Namely, you send a current and you generate a magnetic field, then can you see that magnetic field using our technique? And we actually can see it. So basically we make samples with planar contacts, and then we send in a current, and we do something called as differential imaging. I'll not get into the details, but when you send the current through the sample, there is a magnetic field distributed across the sample, which is generated by the current, namely the self field of the current. And then using this technique, we image the distribution of the current on the sample surface. So let me give you an example. It's not in a topological insulator, but this is an example. What you see here is a 1 millimeter, half a millimeter crystal of a superconductor, and you have contacts which are sending in current. And this is the image of the field BZXY is the magnetic field distribution which is generated by the current. You can see that there is a bright edge and there is a bright region and there is a dark region in this image. The bright region actually corresponds to the positive part of the self field which is generated by the current, and the dark region is the negative part, namely the field which is going into the plane of the page or plane of this surface, which corresponds to the negative part of the self field. The field that is coming out is bright and the field that is going in is dark. And so typical current images actually look like this. They will have a bright and dark contrast. So from this self field, and this is the distribution of the local field which is generated by the current, and we image this sort of a local field. And we can do a numerical inversion, somewhat like an inversion of the Biot-Savart's law, to get the current distribution. So this image shows the self field which is inverted to get the current distribution, and this is actually how the current is distributing across the sample. This is a superconductor through which you can see that the current comes in. There are strong currents on the edges, there is currents also inside the sample, and these regions outside are the contacts. They are carrying uniform current. So this image is actually to give you an idea what you will be seeing when we start looking at the images of the topological insulator. So let us look at Bi2Se3 thin films first. Okay. And so we grew Bi2Se thin films on STO substrate, and you can do magnetoresistance measurements, and these magnetoresistance measurements show very nice weak Anderson localization. You can do a fitting through the popular HLN equation, and you can get the phase coherence length. The phase coherence length is about 48 nanometers at 4K, and decreases to about 20 nanometers at 15K. They were stoichiometric as well as epitaxial films that we obtained on Bi2Se3. So now what we do is that we apply this imaging technique to actually image the current distribution in this thin film. So this is the first image that you see on the left here is an image of the thin film which is carrying current. And this is directly the current distribution that I'm showing here. And what you can see is that there are very strong currents which are flowing along the edges. And there is almost negligible current in the middle of the film. And if I draw a line and measure the current distribution, you can see that the edges of the film carry a lot of current, about 1600 amps per centimeter square. And these currents decay very rapidly, exponentially down as you enter the bulk of the film. The bulk of the film does not have zero currents. Okay, it is much lower, about 200 amps per centimeter square. Okay, so the current distribution, actually, if you recall, the scanning squid images also showed that there is very large amount of currents located on the edges, and there are currents in the center of the sample also. Okay, but these are almost like one-dimensional wires, channels of current which are flowing, almost one-dimensional wires of current which are flowing on the edges. Okay, so where has the 2D nature of current gone? You should have seen a current sheet which is flowing, but instead of a current sheet, you see actually wires of current, very strong edge currents which are flowing inside this 3D topological insulator. Okay, now what we did was that we applied weak magnetic fields, and as we applied, so this is a three-dimensional map of the current distribution. You can see that on the edge there is strong currents, and then it decays down to about 200 amps per centimeter square in the center, and this is uniformly present all across the film. Now if you apply a magnetic field, what you find is that the currents on the edges are slowly decreased. Okay, you start decaying out, you start decreasing the currents which are on the edges, and so this is 40 Gauss, and at 100 Gauss you get almost a uniform current distribution all across the film. So this is quite amazing, is that we could see the current distribution. It becomes uniform, almost uniform across the sample with slight non-uniformity along the edges, but then from a non-uniform current distribution with slight application of magnetic field, we actually start getting an almost uniform distribution. So you can see that this peak at the edges, as you increase the magnetic field, decreases, and then you get almost a flat top current distribution across the sample. But this is in the thin films, you have to apply a weak amount of magnetic field to actually get this sort of a 2D sheet of current to flow inside the sample. Okay. Now let us go over to imaging the single crystals. And we looked at a variety of single crystals, but I will just tell you about the results on a 69 micron thick single crystal of Bi2Se3. You can see the nice DHVA oscillations which correspond to the surface states. You can do a fitting, and you can show that the surface states is actually sitting below in the bulk gap of the material. Okay, so these are actually conduction from the surface states in Bi2Se3. And so this is as far as the basic characterization of the crystal is concerned. Okay, and let us go to the imaging of this surface state. Okay, so if I go to the single crystal and image it, this is at 15 Kelvin. This is the surface of the single crystal, and you can see the bright region is all over the crystal uniformly. If I convert this into a map of the current density, you can see that the current density is uniformly blue all across the sample surface. This is the line profile of the measurement of the current density, and the current density you can see is almost flat all across. So it is actually a 2D surface sheet of current which is present on the thin single crystal. On the single crystal, you can actually see directly the conducting surface state as a 2D sheet of current which has a very high current density. If you integrate this current density across this, and integration of this current density across this length into the thickness will give you the total current which is flowing. And from this, you can get the thickness of this surface sheet to be about 3.6 nanometers. So the topological surface state on the single crystal is about 3.6 nanometers, which has been seen from other experiments also to be of this order. So we are actually looking at the conduction through a 2D surface state on the single crystal. Okay. But now as you increase the temperature and keep on measuring the current, you see that the current on the surface progressively decreases. As you increase the temperature, the height of this current density on the surface actually goes down. And if I image this current density, you see something quite amazing, is that the current actually not only decreases in strength, but it starts breaking up into patches. There are patches of blue regions which are high current regions, high current carrying regions, but there are lower conductivity regions which are appearing in the sample. And as you increase it, it actually becomes more and more. So the region which has uniform high current density starts breaking up into patches as you increase the temperature, and the amount of current on the surface actually starts decreasing. So we analyze this, and where is the current going from the surface then? So we analyze the field distribution. If you look at the magnetic field distribution on the surface in this cell field, at low temperature, this is the field distribution. But as you increase the temperature, the field distribution actually becomes more and more flattened and spread out as you increase the temperature while you are measuring the sample. Okay. And the way we analyze this cell field distribution is that we consider the total current is made up of a fraction of the current which is flowing on the surface, which is called Fs, and the fraction of the current which is flowing in the bulk. So we consider 2D surface sheets of current, and we consider 3D bulk current, and we calculate the field which is generated by these surface and bulk currents for different fractions. Okay. And the cell field is actually fitted with this sort of a model where you have surface current and you have bulk current. And you can see that if you can fit these, and you can actually measure how much is the fraction of current which is on the surface, how much of fraction is in the bulk. So at low temperature, we get about 82% of the current which is flowing on the surface as 2D surface sheets. And as you go only 18% through the bulk, but as you increase the temperature, this fraction completely reverses. You get about 80% through the bulk. Because of the presence of selenium vacancies, the bulk conductivity increases beyond a certain point, and you get the conduction through the bulk rather than through the surface. So the current on the surface decreases because more and more current starts channeling through the bulk, and this we see clearly. So now that we have measured this Fs and Fb, okay, the fraction which is flowing through the 2D surface states, we can plot this as a function of temperature. If you measure this fraction as a function of temperature, you can see that this fraction is decreasing monotonically. The fraction which is through the topological surface state is decreasing monotonically. However, above 70 Kelvin, there is a sharp decrease in the surface state contribution, and this becomes much less above 70 K. And above 70 K, if you look at the bulk fraction, it increases as is expected, because okay, so this increase in the bulk fraction above 70 K, we have done some interesting recently we have done some interesting non-contact conductivity measurements which pick up coils, and we were able to show that the conductivity above 70 K becomes a thermally activated conductivity. Below 70 Kelvin, it is all topological surface dominated, so which matches well with our measurements, which shows that there is a very high surface conducting fraction. But above 70 K, the thermally activated conductivity is coming from the selenium vacancies in the bulk, and we believe that there is a band generated by the selenium vacancies about 70 Kelvin below the bottom of the bulk conduction band, and there are excitations across this which generate this thermally activated behavior. So at 70 K, the moment the bulk starts conducting, you have this large drop in this 2D surface conducting fraction. And this drop in surface conducting fraction actually corresponds to your uniform conducting 2D surface conducting state breaking up into smaller and smaller patches. Okay. So if you recall, you can measure this region which has the uniform 2D surface state. You can measure the area of these blue regions, which are the high conducting surface states. and those are shown as open circles. Okay, and if you measure them, the region, the 2D conducting region, as a function of temperature, you actually see that this area, the fractional area which contains the 2D surface state, that is decreasing monotonically as a function of temperature. But above 70 Kelvin, there is a rapid drop in this fraction, and this is the point where the conduction, you actually break up these regions into smaller and smaller patches. As the bulk conductivity increases in the sample, the system, actually the 2D surface conducting state, breaks up into smaller and smaller patches. Okay, so now we wanted to actually look at this curve. If you look at the blue curve, the blue data points, or this surface conducting fraction, which is measuring the surface dominated conductivity from the topological surface state, we wanted to analyze this, and we were thinking of it in terms of the electrons which are present inside the system. So one is 2D surface state electrons, the Dirac electrons which are present. But above a temperature which is the bulk gap temperature, which is about 0.3 eV, you will have also normal electrons which are generated because of excitation above the gap. So above a temperature Tc of about 3000 Kelvin, you will get a dominance of normal electrons which will dominate over the Dirac electron surface electrons. Okay. And from Ginzburg-Landau theory, the order parameter, if there is a critical transition temperature where there is a transformation, this order parameter should go as T minus Tc raised to half. Okay. So here is a fit of the data of this fraction, okay, with a critical temperature of 3481. That is actually not fitting the data. But you can see that this fraction actually fits very well with a critical transition temperature of 220 Kelvin. And we believe this is the mean field transition temperature because along with your surface conducting fraction, there is a normal fraction which is appearing in the bulk because of excitation of the carriers in the bulk by the selenium vacancies. So the actual mean field transition temperature is actually 220 Kelvin, and this actually fits the initial part of the data where the data is surface dominated by the topological charge carriers. That is where you have this fit, so your surface conducting fraction actually behaves like an order parameter. However, above 70 Kelvin, you see a very sharp break in curvature. And this surface conducting fraction actually fits to another form, okay, where the system is breaking up into these small patches. It actually fits to another form, okay, where FST has this form of a behavior. Okay, so the critical transition temperature now changes from 220 Kelvin to 70 Kelvin. 70 Kelvin is the point where the system is actually becoming bulk conducting, and this is also the temperature where you are going from uniform 2D surface states to this patchy like network. So what we suggest is that there is a disorder induced Griffith phase like transformation at 70 Kelvin. So below this 70 Kelvin, you have uniform Dirac like surface electrons which are present on the surface. These are 2D surface electrons. At 70 Kelvin, you are breaking up the region into these patches where the light blue regions contain normal electrons which are being generated by the selenium vacancies in the bulk. And so you have two different fractions of electrons. One fraction are the Dirac surface electrons. The other fraction are the electrons which are generated in the bulk. We don't know how they interact, but we feel that the breaking of the system from this uniform 2D surface state to this patchy like network happens at where the bulk electrons, exactly where the bulk electrons are being excited in the bulk of the system generated by disorder. And because of this, the transition temperature is different from the bulk transition temperature, okay, at 70 Kelvin. So the system actually first breaks up into these patches, and then they break up further as you go to higher temperatures. And this is what we call as a Griffiths-like phase transformation that we see as you go from this 2D surface state into a more inhomogeneous like surface state inside the system. Okay, so this comes out as you as you look at the current distribution in the topological system or in this 3D topological insulator. And what we believe is that similar thing happens in thin films, because in thin films we feel that because of the presence of a lot more disorder compared to single crystals, it already has a Griffiths transition temperature which is much below 70 Kelvin. Okay, and it is far lower than 70 Kelvin. So the system is already in these localized regions. Okay, so in the bulk of the system you already have these patches of local order which is surrounded by normal regions of electrons. So the current actually essentially channels through the edges and doesn't flow through the bulk of the system, because, and that is what destroys, and only very low amount of current flows through the bulk because you don't have a uniform conducting region. So there are these local pockets of order which are present in a medium of normal electrons, I would say, which are generated by disorder. So therefore the current actually channels through the edges, and as you apply a magnetic field, it actually causes suppression. Time reversal symmetry breaking actually causes a suppression of these edge currents, and even these currents are decreased, and it tries to make the conductivity of the system a little bit more uniform. And so this is the reason why we believe that in thin films of 3D topological insulators, you never see the 2D nature of the surface state, because of the presence of disorder, it actually brings the 2D system, the 2D state of electrons already goes into the Griffiths-like phase. So with this,
Satyajit, you have another 2 minutes.
yeah, I am done.
Okay.
So I come to the summary. So basically, from our study of imaging of these thin the single crystals at low temperatures, it has a uniform topological 2D like surface sheets, which you can see, which are about 3.6 nanometers thick. With temperature, actually these high current density area fraction behaves like an order parameter. It shows a sudden decrease at 70 Kelvin where there is an onset of bulk conductivity, and the system breaks up into patches, okay, where there is local order surrounded by normal electrons. So the local ordered regions which have short range order, which is the Griffiths phase, the local pockets with short range order has the Dirac-like electrons, and surrounded by the normal electrons which are generated by disorder. And we feel that this is also the reason which destroys the 2D surface states inside Bi2Se3, the observation of 2D surface current sheets in Bi2Se3. So with this sort of, I would like to end my talk here. Thank you. Yeah.
So thank you, Satyajit, for a very interesting talk. So now the session is open for maybe 2-3 questions.
Can I ask a question?
Yeah, please.
Yeah.
Yes.
So first of all, Satyajit, this beautiful data is extremely impressive quality of data. Now, I have several questions, but I will ask a couple of them.
Okay.
One thing is that what are the how much current are you passing in terms of not current density, but in terms of current?
35 milliamperes.
I see. And the initial data that you showed on the superconductor was what, niobium diselenide or?
No, this is a potassium doped barium iron arsenide that we have recently published in PRB, where this is in barium iron arsenide, potassium doped barium iron arsenide.
I see. Because one thing that I was curious to know in the data, you have a significant amount of current which is also flowing in the bulb.
Yes,
now,
yes.
Why is that? Normally, you expect the current to flow within penetration depth on the surface.
But actually what happens in this system is that as you increase the temperature, we have looked at this close to the melting transition. There is a melting transition in this system. And once you are close to this melting transition in the system, you see that the current distribution, because the conductivity of the edges is no longer very different from that of the bulk, and therefore the current actually zooms into the inside of the sample, and then you see this melting patches and so on. It makes the current distribution.
Melting means, is there a magnetic field in those experiments?
There is a magnetic field. Of course, there is a magnetic field.
I didn't realize
so that. I didn't get into that aspect because I just wanted to give an idea what is the image that you will see. What is the nature of the image of the current that you will see?
And one final question about this thin film data on bismuth selenide.
Yes.
TiO3. So in a thin film, I don't know this very well, but what I read is that you have the top and the bottom surface.
Yes, if you are
And,
below 5 nanometers,
I
then
see.
you actually cause a hybridization of the surface and it lands up into a trivial insulator.
Yeah,
You don't
that
get
is
that.
not the case here.
This is 30 nanometers.
I see. Okay. Thank you.
Okay.
Okay.
Oh, thank you.
So, any other question?
Rajendra, I raised my hand. Can I ask a quick
Yes.
question?
Yeah. Please, please.
Okay, so the Shota is very interesting and very nice talk. As Pratap said, the images are great and very instructive. The quick question is your claim on the Griffiths phase and looking at the edge current even in your thin films.
Yes.
Seems to go against, transport measurements, even what we did. I mean, we did these kind of measurements in samples grown by Nitin Samarth on bismuth selenide. And it was 10 nanometer thickness. And we saw perfectly two-dimensional behavior, both in weak localization measurements as well as other kind of measurements that we did.
So how did you confirm the 2D nature?
From weak localization, you can easily fit the kind of weak localization behavior that you see. You can gate them by applying the strontium titanate gate from bottom. You can actually gate and look at the completely two-dimensional behavior. So I was surprised that you saw a edge propensity of the edge current. And
yes.
so whether this is a question of specific or very material specific problem is my question.
No, this is actually we have been looking at, there have been other imaging also. People have done other imaging in thin films in other systems. In Di2-Se3, there have been quite a few other techniques, and all of them see this predominance of the edge current. Okay, now what we would like to mention, if I can just go back for a minute on this slide, somehow I'm not able to come out of it. If I go back to this, yeah, if you see this, if you see the distribution of current, it is not, you don't see, it is not actually one dimensional. Like what other people may have missed is that it looks like as if there is only current on the edges. There is current on the edges and there is a lot of current on the edges, but it is also there in the bulk of the sample, in the center of the sample, which is about 200 amps per centimeter square. So it is not, it is a 2D like nature, but it is not a uniform current. It is not a flat top current that you should see. You see large current on the edges, which decreases in the center of the sample. So in that sense, current is flowing all throughout the surface, but there is more current on the edges versus the away from the edges. That's what we wanted to mention, that you don't have a flat top uniform current which is flowing.
Okay. I mean, sorry, Rajendra, if a very fraction of a second comment, whether the large increase in current is because of the potential electrostatics of the edges, because this has been observed in a number of cases, say in bilayer graphene, for example, as well, that when you have the edge, because of the electrostatic nature of the edge, you see an accumulation of current. So the question is whether this is something to do with really the Griffiths phase or simply because you have an edge, the electrostatics makes you give a large current there. Okay.
No, the Griffiths phase starts away from the edges. What we see in the Griffiths phase is that the Griffiths phase in the single crystals, for example, this Griffiths phase starts in the center of the regions of the sample, away from the edges, well away from the edges. Hello?
Okay. So,
Rajendra, can I ask one question?
Gautam Sheet has raised his hand. So, you may ask the question.
Yeah. I mean, so who? Gautam Sheet or me? It's Seti.
Yeah, Gautam Sheet.
Okay.
Yeah, so Satyajit, this is a question regarding the characterization of the crystal and the thin film. Is it known the position? Where is the position of the Dirac point with respect to Fermi?
Yes, so we did a crude sort of estimate. So what we did was we did the fitting of this DHV oscillation, and then you get the surface density of electrons from which you can determine the Fermi energy of this KF. You can get the KF, and then Of course, we didn't do RPEs on these crystals, but if you take Bi2Se3, they have a 300 milli electron volt gap between.
I'm asking for your crystals.
Yeah, this
because
is for our
selenium
crystals.
frequency.
Yeah, but okay. I don't think it is 0.1, 0.2 eV below the bottom of the conduction band. The KF that we get is 0.1, 0.2 eV below the conduction band. So they sit in the bulk gap of the system. These are surface states which are sitting deep in the bulk gap of the system.
Okay, so does that also mean that if I do these experiments, when you have the Griffiths phase, let's say local probe experiment like STM, then I will see the Dirac point, the Dirac cone at certain points, but not at other points?
Not, I think at high temperatures, if you are able to do it at reasonably high temperatures above, in our crystals, we got it at above 70 Kelvin. So if you go above 70 Kelvin, it depends on what is the disorder concentration in your sample. But you should see that you will have localized regions where you will see this Dirac spectrum in localized regions compared to other regions.
Absolutely. Okay, thank you.
Okay, so Dr. Tirupataya Sethi, you may ask.
So it's more or less similar to what Gautam Sheth asked. So did you cross-check with a system without conduction band contributing to your resistivity?
Without conduction band? Sorry, I didn't understand.
Did you cross? I mean, there are certain systems where there is no conduction band below Fermi level.
Oh, okay.
So did you cross-check? Yeah.
No conduction band below. You mean an insulator or something? Or I don't.
No, I mean they tune the Fermi level such that this conduction band.
You are talking of systems where you have actually made the bulk absolutely insulating.
Yes, exactly.
Yes,
Did you cross-check?
So that is something that we are currently doing. There are certain systems, good single crystals we have managed to hold on to from some collaborators abroad, and they have supplied us the crystals. We are doing that on those crystals.
Okay.
Okay. So, Satyajit, I have just very small question related to the vacancy concentration. So, has it been in the literature calculated how much is the typical selenium concentration, vacancy concentration?
So the vacancy concentration, I think they have done positron emission studies on these crystals, and 10 raised to 13 or 14 per centimeter cube, something of that. I'm not. That is the level of order.
Yeah, but that's quite low actually. 10 to the power 13 or 14%.
Yeah, I am just quoting out of my head. It could be slightly higher, but it will be 14, 15, I think.
Okay, thank you. So thanks for this very interesting talk, Satyajit. And thanks again. So now we have the second speaker for today's session is Dr. Tirupataya Sethi from SN Bose Center, Kolkata. And he is going to talk about the electronic structure studies of FESI, a chiral topological system. So, Dr. Sethi.
Yes, thanks, Rajendra. Also, sorry that I changed my title recently, so it will be the new title. While making my presentation, I thought maybe let's make some general title. So the new title would be like, okay, am I audible?
Yeah, you are audible.
Oh, thanks. So the new title would be like topological systems of beyond Weil and Dirac quasi-particles. So yeah, so I am from SN Bose, as you explained. So my talk would be like this. So first I'll give a brief introduction to, first of all, let me thank the organizers, the other organizers, Manoranjan, Priya, Atin, and also for giving me the opportunity to present our latest work in this beautiful stage. And also let me also thank the national organizers for giving us this opportunity to host this prestigious conference from SN Bose. Yeah, so this will be the outline of my presentation. So first I will be giving introduction to topological quasi-particles. And then, so since I will be presenting mostly the ORPES data, I will give some details of ORPES technique. And then, so initially I changed the title with the hope that I can present not only iron silicide, which one of my PhD students published recently. I thought I could also present some data from this platinum bismuth too. But later on, since the time limit, I don't know how much time I would take, so I skipped it. But this is already available in arXiv. It's a very beautiful paper. And here we could identify 6-fold Dirac fermion near R point, and which actually becomes like several Weil fermions under magnetic field. So many details are there in this manuscript. If you are interested in, you please go through that. But today's talk, I will be mostly concentrating on, let me take the pointer. Today's talk, I will be mostly concentrating on these iron silicide results. So this is Shushmita. So he's a PhD student working with me, and today I'm presenting her work mostly. And we have very good collaboration with IFW Dresden, people from IFW Dresden. And as we study as the systems, these guys also support multifold. Support is multifold, and for this iron silicide, we got very good calculations from Avadesh and his teammate, Anumita Bose. And the results that I'm presenting here were measured in PSI, SLS, I think I missed it, and also measured in Helmholtz-Zentrum Berlin, BASIC. So funding, yeah, this inter-faculty funding was really great to visit these beam times. And also to visit PSI, I took the help from DSTJ and CSR project. And I'm also thankful to my institute for the startup grants. So we all know all these details, but let me start again from the basic, just to have some flow. So we all know the band insulator has a big gap between conduction band and valence band. And when you apply spin orbit coupling, in certain conditions, they come together and there will be an overlap between conduction and valence band. And if there is no symmetry protection at these overlapping points, there will be hybridization, and then they tend to open a gap. But surprisingly, now what happens is valence band will go up and conduction band will come down, which is a condition to develop a surface states, topological surface states. And there are many results which actually was invented. Maybe RPS was found in 2008 or 2007. So I have taken from 2011, which was a bit beautiful to present here. So here is a Dirac point. An important point about this Dirac point is that this is only protected by time reversal symmetry. And you can open a gap just by breaking this, the time reversal symmetry. That means it has only twofold degenerate point. According to the latest understanding, such twofold degenerate point has been being called Weil fermion. So I don't know whether one can still call it as Weil fermion rather than Dirac fermion. Maybe theoretical people can advise. But for me, it looks like simple Weil fermion rather than Dirac fermion. Okay, so now again going back to the previous condition, again conduction band is there, valence band is here. Now these crossing points are being protected by symmetries. In such case, you are ending up with the Dirac semi-metal, and here is two Dirac points in one brilliant zone, and those are connected by these surface Fermi arcs. Different colors represent different spin orientation. So, and they look like this along kz direction. This is kz axis, and this is kx, ky axis, and this is energy. They look like this. And when you see and here, these Dirac points are protected by, in fact, two symmetry points, time reversal symmetry and inversion symmetry. And this is the bulk Dirac point, and these are the surface states. And these surface states are actually connecting the bulk Dirac point. So here is the surface states, and there will be the bulk point. This is when you project them, and this is the spin orientation taken from this paper. So in fact, unlike what I said, surface Dirac points or Weil points, whatever it is, these three-dimensional or what you call bulk Dirac points are not always topologically non-trivial. So we found one of such case. This was a famous 3D Dirac point. So here you can clearly see a gapless Dirac point, and when we dope, it's not even like doping; it's just disordering, like replacing phosphor by arsenic, which is an isovalent substitution, and there is a gap opening clearly. So usually when we call topological, if it is not disturbed, the Dirac point is not disturbed, then we call it as topologically protected. But just by disorder, it's being disturbed. So I think it's not always topologically non-trivial. These 3D Dirac points. This is one of those examples which we studied earlier. So now let's take this 3D Dirac point or fermions, and then if you break the inversion symmetry, then you end up with 4 Weil fermions. And if you break the time reversal symmetry, you end up with 2 Weil fermions. Okay, here this is protected by inversion symmetry, and since here inversion symmetry is broken, you have mirror symmetry, which will give you 4 while fermions. So in principle, one should always be having minimum 2 while cones for a given Dirac point. So latestly, Broadlin has come up with a very nice paper, which actually generated a lot of interest to the people like me. So they predicted not only twofold, and then I forgot to tell you, this Dirac point is fourfold degeneracy. So here it has a fourfold degeneracy, and while point has twofold degeneracy. And apart from that, these guys predicted threefold degeneracy, sixfold degeneracy, and eightfold degeneracy. Fermions, I don't know what to call them. And they look like this. And they mentioned, like, this depends on the space groups. For example, this 198 space group will generate sixfold degenerate fermion at the R point, and in the presence of time divorce symmetry. And these are the three symmetry operators which protect them, which protect this sixfold degenerate fermion. So after seeing this paper, there are lots of researchers jumped on it, or maybe parallelly were working on it. So then, yeah, we started also seeing parallel working on it. So we found, yeah, I'll come back later. So now let me start with the facilities that we measured. So we measured, this is the aerial view, top view of Bessie synchrotron, where we measured some of the outputs measurements. And this is PSI or SLS synchrotron facility. It's also top view. So this is how I have taken a pictorial image or schematic image from one cube output station. This is your analyzer, and this is where your sample is, and this, from here your synchrotron will come in, and then the photoelectrons will go into this your spectrometer, and they get analyzed here, and finally end up here, collected by the detector. And this is the cross section of the one of the important components of RPS machine. I think many of you know it already. So here you have electrostatic and magnetic lens, which monitor the path and kinetic energy of the photoelectrons. And here they get analyzed, and then finally they fall onto this detector and collected by the phosphor screen. And this is what your raw data, which along y-axis, here along y-axis we have kinetic energy of the photoelectron, and along x-axis we have the takeoff angle. So this is what the raw data look like. And most of this, since this is a surface sensitive technique, we have to always have the very clean surface. So since we work mostly on single crystals, and this is a small technique that we use always. So this is sample holder, and this is a small ceramic rod. In between, we attach a sample using silver paste or any high conductive glue. And then this whole setup will go into the ultra high vacuum chamber, and then we gently knock on top so that we break it or we cleave the sample, ending up with very clean surface. For XPS, of course, this is a 6 degrees of having 6-degree motion of the what you call manipulator, cold finger. So for standard XPS, you don't need to have any degree of rotation, but for RPS, we need to have a minimum 6 or maximum 6. So out of them, 3 are rotational and 3 are translational. If any one of them are missing, means then you are compromising with moving around your 3D balloon zone. And these are the beam lines that with having at 1 cube RPS, you have 1 millieV energy resolution. Energy resolution 1 millieV, and temperature you can go down actually below 1 Kelvin, and vacuum chamber is always better than 10 power minus 10. And at SLS we have this high resolution beam line, and here you have, I think, approximately 8 millieV with the sample temperature, I think less than 10 Kelvin, 10 Kelvin or quite close to that. And it's always, I think, high 10 power minus 11 pressure. So here I schematically showing the momentum space today in Kx, Ky, and Kz. If you think your Kz is sample surface normal, and this is the photoelectron is moving towards your detector, so then you can project that on this Kx, Ky plane, where you have you can resolve your momentum vector into Kz, Kx, and Ky. And here, just by knowing the takeoff angle, you can convert your this kinetic energy formula into your momentum, in-plane momentum and out-of-plane momentum. And finally, you need only these three simple equations to convert your ejected photoelectron into momentum space, Kx, K, and Kz. And this is a representative raw data. How does it look like without any data analysis and all? But here, one tricky thing for estimating Kz values is that you need to know the inner potential, which is not readily available for many systems. So most of the times, this RPS community will represent Kz values in terms of the photon energy or kinetic energy. So another wonderful information that you could get from RPS technique is that you can identify electron correlations, low energy electron correlations. That means the correlations near to the Fermi level. And those correlations are stored in the form of quasi-particle self-energy, having the contribution of electron-electron correlations, electron-photon correlations, and electron impurity correlations, also Magnar and so on. If you think this is the spectral function, your and the spectral function has this Lorentzian function, and your imaginary part of self-energy will give you the spectral width or the strength of correlations, and the real part of self-energy will give you the band dispersions. So I didn't go deep of those because I don't need much of that information. So now let me start so our main topic. So why we need to measure, why we wanted to measure iron seaside? Before we start our measurements, already there were predictions, also some RPS data on cobalt silicide and the rhodium silicide. There they clearly predicted that cobalt silicide can give spin 1 excitation at the gamma point, and also at R point there will be, I mean these are high symmetry points. At R point we'll have a double wide fermion. And these points will have this kind of, for example, the spin 1, if this is a standard wild fermion having spin of the spin of half with a topological charge of plus or minus 1, and spin 1 excitation will have topological charge of plus 2, plus or minus 2, and this flat band will have topological charge 0. And this another interesting fermion with the spin 3/2. This was introduced by Rarita Stringer, and which look like wild, so it is called RSW fermion, which is having a spin of 3/2, this one, and this band has spin of 1/2. And double whale fermion has two points, while points having half of spin. And here I think they separated it apart just to show that both are present at the same momentum and energy position. And here I'm showing the high symmetry points. Your gamma is there, R, X, and M, which you can correlate here. And if you see the Fermi surface map, it looks like this. So you have between gamma and R, of course this is a projected one, you have a surface state connecting these two high symmetry points between gamma and R. So, and then everyone was fascinated to search for this surface Fermi arc. And interestingly, this Fermi arc doesn't close up, so it's open. So at that time, it was very interesting. And these were the RPS measurements. So they could nicely see the Fermi arcs between gamma and R point or M point projected. These were the calculator, and these were the calculator surface states. And this was the RPS data, where they don't show the surface states here, but mostly the bulk bands. And when you come to the electron band structure, this cobalt silicide looks more or less similar to iron silicide. Iron silicide looks more or less similar to cobalt silicide and rhodium silicide, except that your Fermi level is a bit below the topological points. What do you call, multifold degenerate points. So we thought that maybe if as you can see, the surface states disperse quite far. So we thought we could catch them if they are dispersing here. So at that time, we didn't take help from anybody to evaluate to know how far the surface states can disperse. So we thought, okay, iron silicide also could be an ideal candidate to measure. So that's why we have taken iron silicide. Another reason is that already by then there was a very nice paper from Claudia Felser saying that yes, indeed, this is a topological, and they say it's insulator, which I will discuss later. So they say it's a chiral insulator because they found non-zero Berry phase. So this motivated us that yes, we can, in principle, we can find the surface states if at all they are present. So this iron silicide or all these cobalt silicide, rhodium silicide are B20 type structure. B20 in the sense that the symmetry, the unit cell is cubic, but with reduced symmetry. It has no inversion symmetry and also no 4-4 rotational symmetry. And this is what basically the crystal that we measured. In fact, the crystal was very hard. So the crystal grower was need to use a diamond cutter to cut it. This was the XRD, although it's very bad. I was lazy to collect a good XRD pattern, but this explains that the measured crystal is indeed the required, the desired space flow, which is 190 or P23, 198. So on the EDX measurements says that they are within the error bars, the crystal composition is perfect in the stoichiometric ratio, iron Si, without any impurities. And before performing any outpass measurements, we also look for any other impurity atoms present there. And this clearly says that there is no other impurity except from iron and silicide, silicon. And then we also did our resistivity measurements here in SNB. And this looks more or less like a semiconducting profile. And here we see a little deviation, which I'll come later to talk about this deviation. So now let me start discussing about RPS data. So this is the Fermi surface map taken in plane Fermi surface map in the gamma XM. So this is the gamma, the first Brillouin zone, let's say, gamma point where you have finite spectral intensity. And then we moved quite far to reach another second Brillouin zone. I won't say second in the sense it's in the same plane. Actually, it moves up a bit, either up or down in RPS. And this is another gamma point with a different Kz value. And again, this is another gamma point with a different Kz value. So in RPS, when you go away from normal emission to a bit far away, then you actually reach different Kz planes. So then we zoomed in this area and then we again remeasured the Fermi surface. So this is how it looks like. And then this was measured with the p polarizer light, and this was measured with s polarizer light to see the orbital contribution. And in fact, you see that there is a change in spectral intensity, which do confirm that these Fermi surfaces are contributed by multi-orbitals. And here is the definition of what is p polarized and s polarized. So this is your electric field oscillations, and this is your sample surface, and this is your scattering plane, and this is your the entrance slit of analyzer. So so with respect to your scattering plane, we in general define what is p polarized light and s polarized light. Okay, so and then these measurements were actually, this data whatever we collected was in pretty good agreement with the calculations. So this is a Fermi surface map for the bulk Fermi surface map, which is in good agreement with the experimental Fermi surface map. And then we made band dispersions along, I think this one is along gamma m. Yeah, I think somehow it's missing, but I think this is along this direction, gamma to gamma m0 direction, this one, and this one was this direction. So as you can see, we also overlapped the spin polarized band structure, the band structure with spin orbit coupled band structure overlapped on top of it, which matches very well. So the experimentally obtained band structure matches perfectly with the calculated band structure. And it's the same in both cases. And here we are also showing band structure without SOC and band structure with SOC. Although there are no quite drastic changes, but there is a little bit of splitting in the bands with SOC, with the inclusion of SOC, which I will come later. And then we will, in outpass measurements, we can also measure along Kz direction just by changing the photon energy in the normal emission position. So this is such a Kz map measured in the gamma X Rm direction. And yeah, again here we have a good spectral intensity at gamma and no spectral intensity at R. So and then we made band dispersions along this direction, which I showed here, which is in very good agreement with the calculations. And this is along this direction. Okay, so that means that whatever we observed from RPS is matching very well with the bulk band structure that we calculated. And interestingly, what we did, we also measured along MXM direction, where we have two bands. It's because there are no other bands contributing here, unlike here. It's a very complicated band structure, But along this direction, it's a very simple band structure. So as you can see here, there is a splitting, band splitting. Initially, we did not understand why there are two bands, although our without SOC band structure shows only one band, as you see here. Along XM direction, there is only one band dispersing from XM. So initially, we didn't understand, but later on, we realized that that's how we actually calculated SOC band structure. After calculating SOC band structure, we realized that this gap is actually due to SOC splitting. And this gap matches very well with the calculated band structure. And in fact, this has the implications. When you have no spin orbit coupling, as predicted earlier, at gamma point you have spin 1 excitation, and at R point you have double wave fermion. But if you include the spin orbit coupling, now it changes. At gamma point you do have in fact RSW wave fermion instead of spin 1 excitation, and at R point you have now spin 1 excitation. So, so we from this study we understood that while especially discussing about these transmetal monosilicides, one should in fact do consider the spin orbit coupling effects rather than just by going without SOC. And now let me come back to our resistivity measurements, why we had to do it. As I showed Claudia Felser's paper, not only that, in many papers, it was predicted that these systems are in fact insulators or semiconductors. And when we did resistivity measurements, it also suggested us that this is an semiconductor. Of course, the band gap was very small, 35 millieV, but at Helmholtz Zentrum Berlin, with the energy resolution of 1 millieV, 35 is really very big gap to observe. But this map was taken from Helmholtz Zentrum Berlin or BESI, where we don't see any gap. This is in fact the Fermi surface, so there is no gap. So then we thought maybe we were wrong in measuring resistivity, but when we compared with the existing literature, this is okay, not that bad. And there was recently there was another paper which says that in fact at around 19 Kelvin it becomes a metal, and they suggested that it's because of the topological surface states and all. Of course, that was another motivation for us why we wanted to study this. So this study says that there is something messy. So then we wanted to analyze thoroughly what's happening here. Then we started fitting the activation formula, temperature range by range. So first we did fit between here and here, between 70 and then 170 or 150. Here we got around 35 millieV. And then we keep on changing the range, and we fitted using this activation formula. And then as we go close to the 10 Kelvin or so, the energy gap is decreasing, and which is almost like negligible, 0.5 millieV. And also as we go away from 150, the energy gap is now becoming like even lesser than that 0.3 millieV. And at around 220, this in fact is becoming like metallic resistivity. So that's how, I mean, that clearly explains why we don't see a gap there. And also this is not indeed an insulator or semiconductor. It depends at what temperature you measure it. Okay, and then there were some papers discussing that electron-phonon coupling could be the reason for this. So since RPS is a very good technique to identify any of such coupling, so we immediately started analyzing spectral waves for this band. And this is what the spectral wave plotted as a function of binding energy, and which indeed shows like electron-phonon behavior. And we did fit using Eliasberg spectral function with the inclusion of Debye model, and which gave us a Debye energy of 80 millieV. That is in good agreement with the other phonon calculations on this system. So although we don't know exactly, maybe this, we also know that iron silicide is one of the early systems that Moria has given the famous theory of spin fluctuation. So maybe spin fluctuations also could be the origin for this very strange resistivity behavior, but also phonons have significant contribution for the same behavior. And indeed, we also know many systems, for example, cuprates, I think it's the same theory, either phonon or spin fluctuations are playing for their strange metallic nature, and would be the same theory here as well. So now let me go back to the important point of this study. So, okay, good. So we initially wanted to study this system to see the topological fermions. But then, so we we did not see any of them. So then we need help from theory people. So immediately I contacted Avdesh because I already know him that earlier he calculated on cadmium 3 arsenic 2, and I had some discussions with him earlier as well. So I thought he could do. Then he immediately gave the calculations, and his calculations suggest that they don't disperse downwards, but they're actually above the Fermi level, much above the Fermi level, around 0.5 milli or 0.5 eV. And his calculations suggest that there are some other Fermi arcs, Fermi arcs not, but Fermi surfaces, which look like that. These are not the topologically non-trivial, but those are topologically trivial. As you move away above the Fermi level, they become a closed loop surface states. But unfortunately, we could not see them as well. Could be maybe because of the low scattering cross section, or maybe these bulk bands are dominating the surface states. You know, we could not see them, but indeed we should be able to see them. And if we go to 0.55 eV above the Fermi level, we can indeed see the anticipated the Fermi arcs. Of course, our place cannot detect them. So with this, I come to a conclusion that finite spectral intensity on the Fermi surface map actually suggests that FESC is not an insulator or semiconductor, but at low temperature it acts as a metal. And anomalous temperature resistivity could be due to strong electron-hole interactions. Of course, also one should think about spin fluctuations as well. And importantly, one must consider this S4C effect while talking about the physics of multifold fermions in these transmetal monosilicides. And there were early papers suggesting that, even the calculations were suggesting that this FESI is a topologically trivial system. But we do contradict to their predictions, and we say that in fact, this is a non-trivial topological system, at least from the calculations point of view. With that, I'm done. Thank you.
Okay. So thank you, Dr. Sethi, for this nice talk. So now the session is open for a few questions.
Yeah.
So maybe I can ask one question. So you have told that this FESI is not a semiconductor properly in that sense.
Yes.
So you see, in different temperature ranges, the band gap is different. Moreover, the band gap is very, very small. So that doesn't fit into the definition of classical semiconductors that we talk about.
People say it's a narrow gap semiconductor. That's a terminology is there for FESI. People call it as narrow gap semiconductor. And in fact, if you see Claudia Felser paper, she says it's insulator. So it's all terminology, yeah.
But the kind of resistivity that you are getting in the graph which you have shown, resistivity versus temperature, that is typical of a metallic kind of range. Okay, because the resistivity of semiconductors is usually, you can say, 0.1 ohm centimeter or something like, or little or higher than that one. But in your case, it is mostly below that range.
I agree. That's why I said semi-conducting light, the profile. I totally agree with you. Okay. I could not say exactly this is semiconductor, but my point was that if it is 35 milli EV, I didn't see from such a high resolution machine.
Okay. So any other question? So if that's the case, then I would like to thank Dr. Sethi for this nice talk. So thank you.
Yeah, thank you. Then should I?
Yeah, you may.
Right? Yes.
So the next talk is by Dr. Abhirami S. from IGCAR Kalpakkam. And so Dr. Abhirami S., is she there already?
I'm here.
Okay,
here.
you are there.
Yeah.
Okay, so she is going to talk about the unusual proximity behavior in bismuth selenide and niobium heterostructures. So maybe you can share your slides and
I'm not able to share the screen. The link.
Oh, you're not able?
Yeah.
Didn't I?
So you can mute yourself, Dr. Sethi. Yeah, Dr. Abhirami Swaminathan.
No, I'm still not able to share the screen. That option is still not available to me.
Okay, you can try.
The
So
icon is
maybe the
blocked.
system administrator can help her out.
Yeah, the share screen icon is blocked.
Please see that there is an option in the lower tab.
Yeah,
So
okay.
there is a green share screen. There is a
Okay,
at the bottom there is a share screen. So maybe you use that one.
I got it.
Yes, I think it's now.
Yeah. One second.
Yeah, it has come.
Okay. Very good afternoon to everyone. I'm Abhirami from Indira Gandhi
So
Center
you
for
are
Atomic.
maybe you can increase your volume, so little bit less audible. Yeah.
Am I audible now?
Yeah, now fine.
Okay. Okay, so I am Abhirami. I'm a senior research fellow in Condensed Matter Physics Division of Indira Gandhi Center for Atomic Research. My collaborators for the current work are Dr. Edward Brook, who initiated the work, Mr. V. Tanikarsu, and Dr. Avdesh Mani, who's my supervisor. I'm very grateful to the organizers for giving me this opportunity. So today I'll be presenting our current work, which is on the unusual proximity between niobium and bismuth selenide heterostructures. I will outline it. My talk will go something like this. I would first like to give a very brief introduction to odd frequency triplet pairing in topological insulator superconductor hybrid systems, because the results that we've obtained seem to point towards the presence of odd frequency triplet paired presence of odd frequency triplet pairing, and then I'll move on to uh, show some of our results and how it could be a possible evidence for it. And then I'll talk about some conflicting results that we've obtained, in which there is a spatial variation in the proximity behavior between niobium and bismuth selenide. So, as we all know, the hello, yeah, proximity-induced superconductivity was proposed by Spencer and Koenig in their PRL paper in 2008, and they proposed that topological surface states in proximity with the superconductor can support superconducting states that do not break time reversal symmetry. Am I? Is the connection still there?
Yes, yes.
Yeah, connection is there.
You can make it full screen.
Full screen. Yeah. Share the full screen.
Yes. No, okay. So that is something that we all know, and that such px plus ipy states on the topological insulator surface states can host Majorana fermions, and caused a great surge in interest in the field, because Majorana fermions could possibly be applied for quantum computation at some point in the future. Now, even though they propose that it's a px plus ipy kind of superconducting state that's present, a later work has kind of showed, theoretical work has showed that it's actually a mixing of S-type and P-type components of pairing that's present on the proximity-induced topological insulator surface states. Even though some earlier works are available, I'm citing Pablo Burset's work because we've taken that as a reference to try and explain our results. Moving on. So yeah, so the paper that we have mainly taken references from is this paper, Superconducting Proximity Effect in Three-Dimensional Topological Insulators in the Presence of a Magnetic Field. Okay, so the main results of Pablo Burset's paper are that when there is an interface between a topological insulator and a superconductor, there is a breaking of inversion symmetry, and such a breaking of inversion symmetry in this kind of a hybrid structure could cause an additional pairing term in the superconducting pairing, which is an odd frequency triplet pairing. Generally, the pairing is of even frequency nature, but because of the breaking in the inversion symmetry, there is an odd frequency term that gets introduced. And what's very interesting about this odd frequency term is that it has been proposed to explain long range proximity effects, particularly in superconductor and ferromagnet hybrids. So such is the kind of the state that we can expect. There is an S-type pairing potential, and then there is a P-type pairing potential with their respective coefficients, strength coefficients. And the paper discusses that at zero magnetic field, it is the S-type pairing that dominates. C1 is much greater than C2. There is a presence of P-type as well, but then the S-type dominates. And as B increases, C1 decreases and C2 increases. And at a magnetic field strength which approaches the chemical potential of the induced superconductivity, there is a flipping that happens. The P-type becomes more dominant than the S-type. So, which means we can expect some kind of a change in the induced superconductivity observed on the TI as we increase the magnetic field strength. That's what we expect. So this is the geometry that they have discussed in the paper. A step-like hybrid structure where a superconductor is partially covers a topological insulator and the magnetic field is applied out of plane direction. So moving on to our work and how it relates to Pablo's paper, what we have done is we have deposited roughly 100 nanometers of bismuth selenide using pulse laser deposition. We partially covered it and deposited it with niobium superconductor, which is type 1 superconductor, using DC magnetron sputtering, which is also 100 nanometers. And we've tried and measured the temperature and magnetic field dependent resistance in linear geometry. So if you notice, current is passing through the entire system and we are measuring voltage across the topological insulator alone, which is not covered by the superconductor, and also on the superconductor, which is sitting on half of the topological insulator. So this is the bilayer and this is the single layer. So most of our results will be on, most of what I discussed today will be on what is happening on this uncovered TI. What is the effect of this proximity on this uncovered TI region? Okay, so the very first striking result that we saw was that at zero magnetic field, this is the zero magnetic field RT measurement, RT measurement at zero magnetic field on the topological insulator while the current is passing across the entire system. We see that there is a spiking that happens in resistance. And this spiking, interestingly, is occurring at the superconducting transition of the niobium, of the proximity coupled niobium, which is deposited on the left side, if you remember, this niobium. And further, we notice that with increasing magnetic field on either of the directions, the spiking still exists and its position keeps shifting in correspondence with the superconducting transition temperature of niobium. But if you notice, there is also a decrease in the amplitude of this spiking. And then very interestingly, at around 1.5 Tesla, there is an inversion of this spiking where the spike becomes a dip. And this happens in both the magnetic field directions. So this result where the magnetic field strength introduces some kind of a sudden change at a particular magnetic field strength in the induced superconducting property is what made us try and explain this based on Pablo Bourset's paper. So if you notice, the amplitude is decreasing and then there is an inversion from spike to dip at around 1.5 Tesla. So we try and explain this based on the competition between the S-type pairing and the S-type component and the P-type component in the pairing. So we know that as magnetic field increases, there is a decrease in S-type pairing strength, and there is an increase in the P-type pairing strength. And we also know that P-type superconducting pairing is more compatible with the Dirac electrons of a topological insulator surface states, which is why they are proposed to host P-type superconductivity when in proximity with S-type superconductors. So we would expect that an S-type pairing will cause an S-type kind of pairing potential on the topological insulator would cause a higher scattering of the Cooper pairs, which could probably be the reason for this spiking. And as the S-type component decreases, the strength of this sudden spike decreases. And when the P-type becomes dominant over the S-type, there is a dip that we observe. This is what we are proposing. But then it does not end here. It gets a lot more complicated. We see that, so all these measurements were done on the bottom pair of leads over here. And we wouldn't generally expect there to be any variation between the bottom pair of leads and the top pair of leads. But what we observed is that when we accidentally measured on the top pair of leads, there is an exact opposite, there is the exact opposite phenomenon that happens over there. There is a dip at zero field in the top pair, unlike in the bottom pair where it's a spike, which is what we observed over here. And as the magnetic field strength increases, just as there was a spike to dip flipping in the bottom pair, there is a dip to spike flipping in the top pair. So it's the exact opposite of what happens in the bottom pair that's happening in the top pair. So how do we explain this was our next concern. Uh, similar similar to what happens in RT is what we observe in MR as well. So if you notice in the top pair, there is a spiking in the MR. We've done from 3 to 10 Kelvin. There's a spiking sort of behavior in MR, apart from the usual WAL that we expect in very low magnetic fields. And there is the opposite behavior that we observe in the low field. We were very skeptical about the results, and we multiple times checked this on multiple samples. Even on flakes, we've done this and we observed the same results. So it's not because of inhomogeneity in thickness or anything of that sort. This is a true behavior. So to try and understand this further, what we did is we made leads on across the entire width of the topological insulator. So if you remember, this is the niobium covered portion of the TI, and this is the pristine TI. I mean, this is the TI without having a niobium covering. So we tried and deposited, we tried and made contacts across the width of the topological insulator, and we tried to see how the variation happens. And this is a striking result that we observed. So as we move from top to bottom, we observe that in the top there is a spiking in the MR, and then as we move down to this T1, there is a decrease in the amplitude of the spiking, and then as we move lower, there is a dip, and then the amplitude of the dip increases when we come further to the bottom. This is what we observe. And we are still in the process of trying to model this based on separation of px plus ipy states to the top and px plus px minus ipy states to the bottom, and trying to see if that could somehow explain these results. We are still in the process. Our future work will include STM studies, low temperature STM studies across the spatial variation across the width of the sample, to see if we can observe a change from to try and see the actual S-type P-type pairing that's happening there. And we'd also like to model this to explain the results obtained, and any suggestions and comments are welcome, because that will really help us with our work. Thank you.
Okay, so thank you, Abhirami, for this nice talk. So are there any questions? So I just would like to ask a short question related to the contacts, because the contacts that you have taken, I assume they are going to play a crucial role in the measurements, because your resistance is also quite small. So what is the contact material in this case on the superconductor and on the niobium?
Copper wires with silver.
Yeah,
copper wires with copper leads with silver paint.
Okay, so you have taken, okay. So these are like, so it's not that you have deposited the contacts and then taken by wire bonding or something.
We thought of doing that, but that would also, I mean, it's essentially the same thing we thought so.
So in both the cases, these are the copper wires, and then there is like a silver paste which you have dropped on top of that and dried it.
Yeah.
Okay.
Anything else?
So,
Rajendra, can I ask you a quick question?
Yeah, please.
So what is the functional dependence of magnetoresistance on your on magnetic field? Is it at very low magnetic field? Is it parabolic?
Very low magnetic field, there is a WAL that we see. There's a weak anti-localization because of the disorder. There's a WAL.
Right. No, but even if you see WAL, I mean, I'm trying to understand what is the functional dependence of R as a function of B, which is, I can see it's WAL because it is increasing with resistance rather than decreasing, with magnetic field than decreasing. But do you know whether it is logarithmic or parabolic?
In our pristine samples, in our pristine BI to SC3 work that we've done before, it's always been parabolic. There's been a small WL correction to the parabolic MR that we've observed.
Your parabolic MR is probably at high field that you're talking about. I was talking
above 2 Tesla, roughly above 2 Tesla, it's a parabolic MR, and we observe a WL within -+2 Tesla.
Okay.
Okay. So if there is no other question, then let us thank Abhirami for this nice talk. So with that, I think we come close to the final talk of this one. So I think one speaker has withdrawn as such. So this is now over to the organizers. So thank you.
Yeah, on behalf of the organizers, I'd like to thank Rajendra for chairing the session. The next session, I think, begins at 3 o'clock. Thanks.